Okay, so how is everybody?
Good. How are you?
I'm good. I'm good. I'm here. I'm ready to talk about physics. I'm excited. Um, okay, so a couple things before I launch into stuff. So I posted the instructions for exam one test corrections. They are optional. You do not have to do them. But if you're interested in getting back a quarter of every point that you missed, which I mean is not nothing, honestly, um, you can follow those instructions. Basically, look at what you missed and tell me why you missed it, or rework the problem, or yeah, those are really the two things, right? Just some indicator that you looked at the problem and thought about it critically, because I think that's important to correct those things in your mind that maybe are not correct. So those are due, I don't know, next Monday, I think. And that I will just add to your test points, I think. Questions about that? Again, it's an assignment in Canvas. It's either an upload or a text entry, just some indicator that you thought about what you missed. Okay, so I'd like to continue chapter 7. In fact, I would like to finish chapter 7. So we've been thinking about rotation. We talked about rotational kinematics. We talked about rotational variables. And I talked about uniform circular motion. So the difference between rotational kinematics and uniform circular motion is rotational kinematics assumes a non-zero acceleration, right? So you're speeding up or you're slowing down. The equations are true for alpha equals 0, but that's a boring case. But if alpha equals 0, then omega is a constant. Omega is angular speed, right? And if that's the case, we have uniform circular motion. So let's talk about that. Yeah, so let me share this screen. That's what I want. Okay, so just a quick reminder of uniform circular motion. If you have an object traveling in a circle, so what kind of object? I don't know. Perfect, there's an object. There's a circle going in a circle. So we can define a couple things for this. We can define a tangential velocity, right? So there's v tangential. We can define a radius for this motion, right? If it really is a circle, then it has a fixed radius. And what is required for this to happen is a force or a net force that points radially inward to cause the keyboard to come up. No, to cause centripetal acceleration, A sub c. Right, so centripetal acceleration is the acceleration that causes circular motion, right? Just by definition. Again, we can calculate it if we can write it legibly. That's what I'm trying to avoid. It's my hand on the thing. Centripetal acceleration is v squared over r. We also said it's omega squared times r, because remember, v equals omega r. Yeah, so some force has to be causing circular motion. I did upload the uniform circular motion pre-lecture video, which turned into a post-lecture video. It's in that I go through this stuff, right? So I actually talk about all this stuff as I write it down, and then you see the derivation of this. Okay, so I want to jump into an example, but I need to find my thing. I'm down a monitor today, 2 instead of 3. Okay, so I want to go back to example number 4. We've looked at this already, I think. There's example 4. There's 2. There's 3. There's 4. Oh, yeah, okay. So this made its way into the pre-lecture video, the uniform circular motion video that is now up. Looks like a block of text here, but again, I'm talking about it the whole time. So the question is, if we swing a 50-gram bucket in a vertical circle, right? So like a Ferris wheel, right? What is the tension at the top and the bottom of the path? And we see that the tension at the top is smaller than the tension at the bottom. And that's because weight is acting down both times. So weight helps us go in circular motion at the top, and weight is acting against circular motion at the bottom. So at the bottom, tension has to cancel the weight and cause circular motion, whereas at the top, tension only has to cause part of it. And in fact, if you slow your rotation too much, at the top of this motion, you'll find that there's some slack in the rope, right? It'll start to actually fall because you can't get smaller than 9.8 meters per second squared, right? The centripetal acceleration has to be at least that, or bigger if the tension is adding to it. But gravity only causes 9.8 meters per second squared if it's acting by itself. So you can't go slower than a critical value. It's the same thing that we found for Damian Walters running through the loop. Turned out to be, I think, root g times the radius of the path. So I wanted to look at this and say, okay, so I've got a bucket and I'm swinging it around in a circle. What if I put something else in the bucket, right? When I do this live, I have a bucket that I put a ball in. Sometimes I've poured water in it, and you can actually swing the bucket full of water around in a circle, and the water doesn't fall out. So the question is, this is here. If I put a ball in the bucket, so let's call it a ball, right? What force keeps the object moving in circular motion? And the answer, just to keep us on track here, the answer is it's not tension, right? Because the rope isn't touching the ball. So I'm saying, let's put a ball in the bucket. So there's my ball. The force that causes it to go in a circle is a normal force. And it's a normal force not from the sides of the bucket, but from the bottom of the bucket, right? There's some normal force here or here. Because again, the ball is traveling in uniform circular motion, so it needs to have a radially inward force causing that. Again, the misconception here is that it feels like the force would come from the sides, so like it feels like the force should be like this, but it's not, right? If there were a force like that, it would speed up or slow down. Okay, let me pause. What questions do you have? Okay.
So the normal force, we didn't like count that in the first question, right?
Right, because we weren't thinking about something in the bucket, we were thinking about the bucket itself. So the bucket doesn't feel any normal forces.
Okay, so just if there's an object in it, then there's normal. Okay.
Yeah, because the force is coming from the bottom of the bucket.
Okay.
So I guess like the air that's traveling with it would have to feel a force, but that's more like a fluid dynamics thing, and that's a little beyond what we want to talk about. Okay, good question. Excellent question. Other questions? Cool. So let's look at, we did this one. Let's look at example number 6. I alluded to this kind of problem last time. I talked about Ferris Bueller's Day Off. The question is, a 1,500 kilogram car drives over a hill with a radius of curvature of 50 meters. We'll get back to that. How fast can the car crest the hill without losing contact with the road? Right? So again, imagine that, I mean, not you, because you are a very responsible driver, but imagine that, someone who is irresponsible is driving very quickly over a hill. And when you go over the top of that, even if you don't go fast enough to lose contact with the road, you feel a little bit of a lift, kind of like going over the top of a roller coaster. That lift is because because you're going over effectively part of a circle. So this radius of curvature is saying, like, if you took this, like this arc right here is part of a circle. If you completed that circle, the radius, wherever the center is, the radius of that would be 50 meters. All right, so just because you're not going through the entire circle doesn't mean you don't need to accelerate centripetally to stay on that path. Does that make sense? So you're traveling part of a circle. So I'm suggesting that while you're traveling that part of the circle, you need to have centripetal acceleration, right? Because the velocity needs to be turning down, right? Because just before this, it was pointed right and up a little bit. Just after this is going to be pointed right and down a little bit. So to change the direction, you need centripetal acceleration. Okay, so the question is, how fast can the car crest the hill? So we're looking for a Vmax. How fast? So we can draw a free body diagram for this, as we are apt to do. There's the y direction, there's the x direction, and the forces acting here are weight and a normal force. Right? And the only other force you could think of is friction, but because we're traveling at a constant rate, I don't expect friction to be a consideration. We'll think about friction in a little bit, but that has to do with a different kind of turning. Okay. So we have our free body diagram. The next thing we always do is fill out Newton's second law. So the sum of the forces in the y direction equals mass times a sub y. The two forces acting here are a normal force and a weight, and it needs to equal m times the centripetal acceleration. Right? Again, how do I know that there's centripetal acceleration in the y direction? Because it's traveling in a part of a circular path in the y direction. Right? That's why I labeled it on the diagram. Does this make sense so far? I'll take that as a yes. Excellent. Okay, so so we can do another line of this. We can say normal force minus mg equals m minus v squared over r. Okay, and again, I know that's negative because it's pointing down, and I've called up positive, so I needed to put that negative in there. Okay, so we're almost there. What defines how fast? Like, what defines the maximum speed? And the answer is, well, the net force here has to point down, right? So the faster I go, I can't make weight smaller or bigger. I can't make weight bigger unless without changing mass. So the only thing that can happen is the normal force gets smaller. So the faster and faster I go over this hill, the smaller and smaller the normal force gets. And when I get to that critical point at Vmax, the normal force just goes to 0. You guys buy that? It's the same argument we made for Damian Walters running the loop, right? At that critical point where he's going just too slowly, the normal force went to 0. Now we're on the opposite side of the curve, right? So he was underneath the curve, so it was a V min. We're on top of the curve, so it's a V max. Okay. So if we plug those two things in, we say the normal force is 0, so that's 0 minus mg equals minus m v max squared over r. Looks like the masses go away. Let's use yellow. I can also make the negatives positives. So I can solve for Vmax here. So what I get for Vmax is root G times R. Look at that. It's the same expression we got for Damian Walters. Isn't that interesting? Am I going to reference his name anymore during this? I don't know. We'll see. Root GR. Okay, so we just need to plug in. Also looks like mass didn't matter, which is interesting. So 9.8 meters per second squared times the radius is 50 meters. What I get for that is on a separate piece of paper. So let's scroll up to that. 22 meters per second. Come on. Which is something like 50 miles an hour. Questions about that? Cool. Okay. So what does that mean? If the normal force equals 0, when you go over that hill, going faster than 22 meters per second, you would feel weightless. You would be literally in free fall, right? Which is why it's a bad thing to do it to your car. What about if the situation we reversed? What if we were going through a valley instead of over a hill, right? That's the next part of this. So if we go through a valley, that's like this, and this our car traveling through with some velocity, and maybe this has some, again, not drawn to scale, some radius of curvature. We could ask before we ask the question here, is there any critical velocity for this motion? Well, what's the slowest I can go through this? 0? Is that a problem? No, I'm just gonna sit there. What's the fastest I could go through this? Well, I mean, as fast as the car can go, I guess. What's gonna happen when you go through quickly though? Well, let's draw the free body diagram. So the free body diagram looks like this. And the two forces here are weight and normal force. But the direction of the centripetal acceleration now is upward, right? Because it's always radially inward. It's always toward the center of the circle. That means that the normal force now is causing the acceleration, just like the bottom of the loop when we thought about swinging a bucket. So that normal force needs to be bigger than I drew it. So let's draw it bigger. Sure. And remember, the normal force is related to apparent weight, which is just how heavy you feel, right? The same thing we talked about when we thought about an elevator accelerating upward or accelerating downward. When you're on an elevator and it starts to accelerate upward, you feel heavy for a second, right? And then it gets to some cruising speed and acceleration is 0 again. So when you go through a dip, you should feel heavy, like pressed down a little bit. It's not because you're physically being pushed down, it's because you're being accelerated upward. So you're feeling your own mass pushing in on you. So we can do this. So the question is, what is the apparent weight? Really all we're doing is solving for the normal force. And there is no critical speed here, but it says let's say we go through a valley with the same radius at the same speed that we found before. Okay, so we could do that. Again, Newton's second law equals m times a sub y. Normal force minus weight equals mass times v squared over r. This time it's up, so it is positive. And I'm solving for normal force, so I just say normal force equals weight plus mv squared over r. Okay. So clearly the normal force is going to be bigger than weight because it's weight plus something, right? So I can plug into this. It's mg plus mv squared over r. Where are those numbers? So I have some mass. It's 1,500 kilograms times 9.8 plus 1,500 kilograms times 22 meters per second squared divided by 50. And what you get for this is 29,400. For our reference, the weight is 15,000. So this is almost twice the weight of the car. And everything in this motion would feel about twice its weight. Does this make sense, you guys? Cameron gave me a thumbs up. Cameron, I'm glad you're here. I got your email just a minute ago about power being out. So either power is back or.
Yeah, I was kind of worried, but it came on like about 15 minutes before lecture, so.
Cool. Awesome.
Yeah.
Glad you're here, buddy. Okay, so I want to talk about one more thing about this example. And that is something that I said a minute ago, which was it feels like you're being pushed down. It feels like you're being pushed down. But you see, there is no extra weight downward, right? That feels like being pushed down. That's something we call sometimes a centrifugal force, which is a word I haven't used yet in this course. That's with an F, right? Not centripetal, but centrifugal, right? Centrifugal force is we call it a non-inertial force. It's something that shows up when you, what's the right way to say it? It's an idea that shows up whenever you're in a reference frame that's accelerating. Well, all I mean by reference frame is like the things around you, right? So in that car is accelerating, right? How do I know? I drew it on the picture, right? There's a acceleration upward. But what you notice is it feels like a force pushing downward. Another example of this is when you're sitting at a stoplight and the light turns green and you accelerate forward. What happens to the hangy down thingy from your rear view mirror? It swings towards you, right? What force, I think I have mentioned this in this course, what force causes that to swing backwards? Well, nothing. There's no force backwards. The only forces on that thing are gravity down and tension forward. It's actually accelerating forward, but it acts like there's a force acting backward. So if you don't account for the acceleration of the system, if you treat it like the system's not accelerating, you have to include this centrifugal force. We will never have to do that, all right? There is no centrifugal force. Same thing as when you turn a corner, right? So instead of a curve that's cresting a hill or going through the bottom of a valley, if we're turning, it feels like we're thrown outward. But that's only because we require a normal force or some force to keep us in circular motion, which is actually accelerating the other way. Let me draw that picture. That's example 7. And if I'm not careful, I'm not going to get to gravity, but it'll be okay. We'll make it happen. So I'm not going to do all of example 7, just enough so that we can talk about the idea. So imagine a car makes a turn on a level road. So how do we draw that? Let's draw it from above. And here's the car. And here's the road. Okay. So the car has a velocity that points that way, right? And that velocity is changing, right? It's following the curve of the road. The road has a radius of curvature. Call it R, sure. Sometimes I use capital R, but and again, so it's traveling in a circle. Maybe it's not going to complete the circle, but it's traveling part of a circular path. And so I can describe centripetal acceleration. Almost trip myself up there. Centripetal acceleration. So let me ask, I'm going to ignore what the problem is asking. You can look at the, solutions to see this completely. I just want to ask this, what force is causing that car to travel in a circle? What force is causing centripetal acceleration here? We could make a list of forces. It's a good place to start if we don't know which one it is. So we're on Earth, so weight is definitely there, right? And the car's not going through the surface of the pavement, so there's got to be a normal force. Do either of those forces cause circular motion here? I can wait.
I'm gonna go with no.
Go. Thank you. Yeah, no. Maybe my leading tone was helpful there. But I mean, so to cause centripetal acceleration, to cause acceleration to the right, I need a force that points to the right, at least partially. Yeah. So if I draw this from behind, that's how you spell behind. What does it look like? Well, it's a level road. There's the car. We're looking at it from behind. How do you know? I don't know. Like there's the taillights. Perfect. Okay, so I can draw these forces. There's weight acting downward. There's normal force acting upward. And the centripetal acceleration is that way. Neither of those forces can cause acceleration, bad acceleration. Okay, so there's got to be another force. The only force that we know that is parallel to a surface is friction. It's got to be friction causing this car to go in a circle. How do I know? How can I prove that it's friction to myself, like conceptually? Well, if this road were covered with ice, the car would not turn, right? The car would go straight and off the road, to the left, right? It doesn't veer into the inside of this path. It veers off to the outside of the path because friction wasn't there to cause it to go in a circle. Here's the second question. So we've got friction. What kind of friction is it? Is it static or kinetic? And in the interest of time, because I've got 12 minutes to get through, I haven't even touched the second half of it. It'll be fine. We'll make it happen. Probably not today. I'll bleed over into the next lecture and it'll be okay. Yeah, what kind of friction? Well, it feels like the car's moving, so it's got to be kinetic, right? Well, kinetic friction is the friction of sliding surfaces, right? Optimally, I don't want my tires to slide against the pavement, right? Optimally, the part of my tire that is touching the pavement is at rest relative to that part of the pavement. Does that make sense? Said another way, when rubber rubs against the asphalt, you hear something, right? It's like a squeal or something. I don't want that to happen. I don't want that to happen to my tires. So what I actually want is static friction, which is really interesting. Yeah, questions about this? Does this make sense?
I have one, Dr. Becker.
Yeah, Craig, what's up?
So static friction is holding the car through the curve, right?
Yeah.
But since the car is slipping, how does that not make it kinetic friction?
So optimally, the car's not slipping.
Okay. So it's overcoming the force of the static friction. Basically the max.
No. So again, if you turn too tight of a turn, right? So if you're going too fast through this curve, then the required centripetal acceleration is too big, and you will squeal, right? You've maybe heard that if you take a corner too fast. So again, optimally, the static friction is big enough to cause this centripetal acceleration, and if it's not, you will slide. Either you're going too fast or you're turning too tight. Maybe the pavement is wet, and that changes the coefficient of static friction. Does that make sense?
Yes, thank you.
Cool. So because we're talking about this, again, we'll see how far we get. That's okay. I want to talk about this next conceptual bit. So it's the same problem, but now we can bank the road. Let's imagine banking the road. What does that mean? Well, the picture from above is the same, but the picture from behind now has a small angle, right? Not a very big angle. There's the car again from behind. No. And the centripetal acceleration, this is the tricky part, is still parallel to the ground, right? Not parallel to the embankment, but parallel to like horizontal, the horizon. So now if I think about the forces acting, there's weight. There can be part of static friction, but there's also part of the normal force. Do you see that? Now, if I tilt the curve toward the inside, right? If I tilt toward the outside, that actually hurts me. But if I tilt toward the inside, then that normal force can contribute to the centripetal acceleration. Imagine a NASCAR track, right? The whole thing is tilted inward. That's so that the normal force can contribute to centripetal acceleration, and the static frictional force does not have to be so big. Does that make sense? There's actually, you could look at a problem like this and say, there is a specific speed at which you do not need the static frictional force at all, right? The normal force could cause all of this centripetal acceleration at a specific speed for a specific radius. Okay, so anyway, this is why you bank a curve, so that friction doesn't have to do all the work. Okay, yes, please.
For the first example, what direction would the static friction be on the free body diagram?
This way,
Okay.
because
Like-
it's the one causing the centripetal acceleration.
Okay, so whatever direction the centripetal acceleration is will be the same direction as the static friction?
Yep.
Okay.
Yep. So that's if it's level. If it's if you have a banked curve, it depends on the speed. If you're going too slow, you actually need static friction to prevent you from sliding down the hill, right? If you're not moving at all, you need static friction up the hill. But generally, static friction will either act down the hill or not be necessary at all if you're at a special speed. Okay. That brings us to the next part of the chapter. What I have 6 minutes. Yeah, let's talk about it quickly. Just a little bit. I won't talk about orbital motion necessarily. I'll just talk about gravity. So I introduced the law of universal gravitation. The law of universal gravitation, which is just that all matter in the universe attracts all other matter in the universe. So there's some F to 1 and F1, 2, just based on the fact that these two objects have mass, right? And the size of that force was proposed by Isaac Newton, and it's the gravitational constant, capital G, times m1 times m2 divided by r12 squared, which is the distance between these two objects. He actually figured out the inverse square law of this based on the necessary centripetal acceleration of the moon. I think he may have known the distance to the moon, and he also knew the period of the moon. So he was able to calculate the centripetal acceleration and notice that it was smaller than the acceleration at the surface of the Earth in a proportion that is inverse square of the distance. Okay, and if that didn't make any sense, don't worry about it. It's interesting to me, but it's not absolutely necessary for the course. Okay, so this is the law of universal gravitation, right? All matter attracts all other matter. We notice it mostly for one of the objects being very large. So the force between all of the stuff on the Earth and the Earth is an appreciable force. The force between two objects in like your room is small compared to the force of the Earth on those two objects. So that is the force that overshadows, right, the smaller forces between things. And that's mostly because G is very small, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, Let's do a quick example. Of course, I just wrote in the space for that example in the interest of time, so we'll make most of this go away. I'll keep the equation. I could have kept that too. That's fine. Okay. So let's say we want to position a space probe along a line that extends directly toward the sun in order to monitor solar flares. Sure. How far from the Earth's center is the point on that line where the sun's gravitational pull exactly balances the Earth's? So this is a terribly impractical example, and I'll tell you why in a second. You probably already know. So we're saying I want to put a space probe somewhere between the sun and the Earth so that the gravitational pull of the Earth and the gravitational pull of the sun exactly cancel, right? Which is a great idea, like, oh, it could just stay there, but the Earth doesn't orbit the sun in a circle, so the Earth's distance is going to change a little bit. Plus, if you put a space probe right there, it would have a different orbital period than the Earth, so it wouldn't stay there anyway. But it's more interesting just to think, okay, where is the point between the sun and the Earth where their gravitational forces exactly cancel? So we're looking for this distance. Okay. So rather than solve this mathematically, and we can, and depending on timing, we may do it next time. Again, the solution is posted. It's basically math that follows from this. That's I want Fs to equal Fg, not Fg, Fe. Right, and I can plug in, give me 90 seconds. I can plug in GMM over R squared for each of those things. I would need to look up the mass of the Earth, the mass of the sun, and I would need the Earth-Sun distance. All right, so that's a little tricky. What I want to ask before we go is, does it need to be closer to the Earth or closer to the sun? Good grief, everything blew up.
Earth.
Why?
Because Earth has a smaller mass, therefore it's got a smaller gravitational pull.
Yep, so you got to make up for it by being closer. That sort of logic is super useful, right? Did it give you the answer? No, but it gave you a gut check. Like when you find an answer, if you're closer to the sun, that's a problem, right? Even if the math worked out, probably means you made a math error or you set up the problem wrong. Okay, so take a look at this problem between now and next time. Maybe what I'll do next time is I'll ask you if you have questions about it. I basically have like one other example I want to work for this, and then we'll move on to the new material. So, unless there are any questions, we'll call it good. Thanks for your attention, and I'll see you guys in discussion.
Hey, Professor, quick question.
Yeah.
On the discussion files page, chapter 7 isn't available yet.
I will post it in the next couple minutes.
All right, sounds good. Thank you.
You bet. All right. Thanks, guys.